Hello, and welcome. Dressed in my cold weather gear today because today the temperature got down to 77 here. Um, no, I have these things. I own these things, and we're running out of costume ideas. So I figured I'd come to you as dressed in the cold, Mr. Foster. I guess. Um, Whatever. Let's get started. So today's lesson, we're continuing with circuits, and we're going to look at. Yesterday we looked at last lesson, we just looked at circuits with just a single battery and a single resistor. We're still sticking with the one battery thing, I guess. But I wanted to talk about multiple resistor circuits, and there's two ways that circuits or that resistors can be arranged in a circuit. There's one which is the one we'll be talking about today, which is called a series circuit, where the resistors are in series. A series circuit looks like this. And notice that the resistors are basically in line with one another, right? The current flows through that wire, through both resistors, and then back into the battery. So those are in series. Now I'll contrast that with the other kind to make a little bit more clear what I'm talking about. It's called, so first one is series, which is what we're talking about today. The next lesson will be on parallel. So a parallel circuit looks like this. Notice that in this circuit, there's some branching, right? The wires go in two different directions. It splits. They go through different resistors, and then they come back together, right? And end on in at the other end of the battery. So this one is in parallel. They're in branches, basically, right? They're on separate branches of the circuit, and that's why they're in parallel. Now, you can have both, like in this circuit, right, where those first two resistors are in series, but they're in parallel with that third resistor, right? So you can have combinations. We're just going to look at just series today and not worry about the combinations. We'll talk about parallel tomorrow, well, in the next lesson, and then we'll go from there. So yeah, series is what we're talking about today. They're in series. Now, how do we deal with circuits with multiple resistors? What do we do here? Like we know how to deal with one resistor. Well, the big main topic of what ties both of these together is figuring out you can take your two resistors and basically turn them into a one resistor circuit. And the way that you do that, you find what's called the equivalent resistance. So the equivalent resistance is just it's if you were to take multiple resistors and turn it into one. That would be your equivalent resistance. You're finding however many circuits you have, you're finding the equal singular resistor that you could stick in the circuit to make it the same overall resistance. It's just the equivalent resistance of however many resistors. You take your many, turn it into one. And that's the idea of equivalent resistance. And basically, you start with 2, 3, 4, and you bring it down to 1, and we know how to deal with 1. So that's how it's helpful, right? You bring it down to a 1 resistor circuit, which we know how to deal with. So that comes with a little bit of a formula. So I'm going to go ahead and pull out the whiteboard. Yes, I thought that was a really funny gag. And also, I'm gonna take off this jacket before I get too hot. So the first thing. You can find equivalent resistance with series and parallel circuits. Obviously, we're working with the series formula today. So, whiteboard time. So for series only, here's how you solve for equivalent resistance. Our equivalent resistance is R with a EQ in the subscript, REQ. And how you calculate that is basically if the resistors are in series. I'll draw a little circuit down here, I guess, right? Positive, negative. We've got one resistor here, two resistors here, three resistors here, right? So this one's R1, R2, and R3. So we can take this circuit here and turn it into a circuit with a resistance of REQ. So it looks like that, where it's just the one resistor. Notice that all three of these are in series, right? There's no branching paths here. That little corner is just a corner. It's not like a branch, right? All of the current still flows this way. And we can draw it like this. So how do we do that? How do we calculate REQ? Super complicated formula here, guys, for series circuits. You take R1 and you add R2 and you add R3. That's all you do for series. You just add them up. You just add them up, and you can replace it with one single resistor like that. It's, like I said, very complicated, very crazy. So I feel like that bears no more explanation. We can just get started with that. And let me erase this really quick. All right. So our first problem, it has a multiple parts and a circuit. So let me draw the circuit real quick. We've got, in this circuit, we've just got two resistors. There's the battery up here with 10 volts. We've got resistor 1 connected to resistor 2. And this resistor here on the left has a resistance of 4 ohms. This one has 1 ohm. All right. So we'll tackle the first question, part A, which says, what is the equivalent resistance of the two resistors? We know how to do that, right? REQ is equal to R1 plus R2. First one, R1, I'll just treat that as the left one, 4 ohms plus 1 ohm. So our equivalent resistance is 5 ohms. Wow, very straightforward, right? So that's our answer to part A, 5 ohms. That's our equivalent resistance. Part B asks us, what is the current flowing through the circuit? Now, let me redraw what we've got now so I can make this a little bit more clear, right? So what we have now is this circuit with the 10 volt battery and a 5 ohm resistor, right? That's what we're left with now. We've replaced our two resistors with one equivalent resistor. And now we're asked for current. And this is exactly like we did in the previous lesson, right? Just using Ohm's law, the 10 volt battery, right, and only one circuit, or only one resistor in the circuit, means that the voltage across this resistor is 10 volts, right? So we can use that to do Ohm's law, V equals IR equals IR. So our voltage across this resistor is 10 volts. We're looking for current, and our resistance is 5 ohms. So divide by 5 on both sides, right? We find that we have a current of 2 amps. Very straightforward. That's our current. So that's the current flowing through the resistor. Now, that's true in both of these cases right here. So obviously, it makes sense that this is just like we did yesterday. It makes sense that the current is 5 amps going through this bottom equivalent circuit right here, right? But it's the same thing for this top circuit. So our current flows from our positive side to our negative side, right? So it's 2 amps this whole way through. Nothing changes about that. The water doesn't go anywhere, right? If we're thinking about our water metaphor, the water's flowing, but it hits one tree, it keeps on flowing, hits another tree, and still going. It's still the same water. None of it's gone anywhere, so our current stays the same. Sure, we lost some voltage here. That's what we talked about yesterday. You lose some energy, the voltage drops as you go across these resistors, but the water that's flowing through it, the amount of water stays the same. We still have the same water flowing through it. The current stays the same. And I guess the way I phrased that segues us into our next question. Part C asks us, what is the voltage across the 4 ohm resistor and the 1 ohm resistor, right? So we're looking for the voltage across the 4 and the 1 separately. Now, we just solved for the current, right? So the current flowing through both of these resistors, draw a little arrow down here, is 2 amps for both of them. And we can use that to do Ohm's law again, just for each of them separately, right? We know the current flowing through them, we know the resistance, so we can use that to find voltage, just using V equals IR. So I'll do the 4 ohm one first here on the left, V equals IR. So we're looking for voltage, our current is 2 amps. Our resistance for this one is the 4 ohms, 2 times 4, voltage is 8 volts. So the voltage drop across our 4 ohm resistor is 8 volts, right? And the voltage drop, V equals IR for the other one, current is 2 amps still. Our resistance for this one, though, is 1 ohm. 2 times 1, voltage is 2 volts. So it's 2 volts across the 1 ohm resistor. Now, remember before, if you haven't noticed something about these two numbers yet, before, in the previous equivalent circuit, right, we had said, oh, we know that the voltage across this single resistor is 10 volts, right? Because if you recall, the battery is 10 volts, meaning that, the way that we take it at least, that this side is 10 volts and this side is 0 volts, right? Our current, or our voltage doesn't change through a wire, so our voltage is 10 right here, and our voltage is 0 on the other side, right? So it goes from 10 to 0, meaning the voltage drop is 10 volts. But what you might have been thinking as you looked at this one before I just jumped ahead and solved the problem for you, so maybe I should have asked this question before, is, oh, well, 10 volt battery, right? So is our voltage drop across both of them 10 volts? Just like it was previously. And clearly, I already did the math and took that question away from you. But it's obviously, separately, it's not 10 volts, right? We said that across the 4 ohm resistor, it's 8 volts. And across the 2 volt resistor, across the 4 ohm resistor, it's 8 volts, and across the 1 ohm resistor, it's 2 volts. So yeah, those numbers add up to 10. 8 plus 2 is 10, right? So our total voltage drop across both of these resistors is 10 volts. So let's look at what's going on here. That should make sense. So just the same, right? It's 10 volts on this side. No voltage drop through this resistor, so it's 10 volts right here, right? That's what we'd said. 10 volts right here, or even write 10 volts, I guess. So let's trace it from the other side. 0 volts right here, right on this side of the battery. And 0 volts I'll write there too, on this side of the 1 ohm resistor. So that makes sense that we go from 10 volts, we go through both resistors, and we get to 0 volts. That makes sense, that checks out. Right? So it makes sense for them to have to add up to 10 volts, right? The drop across this one is 8, drop across this one is 2. So what you're seeing here, right, is that our voltage on this side of the 4 ohm resistor should be 2 volts. And then, obviously, there's just wire connecting these two, so it shouldn't drop at all when we get to this point, which should also be 2 volts, meaning we go from 2 to 0, so that one's a drop of 2. Our math checks out. It makes sense, right? We go from 10, we drop 8 down to 2, we drop the last 2 down to 0, and then we're agreeing with the edges of the battery. It all checks out. Heck yeah, very nice. Now, the math checks out there, but I kind of wanted to show you a picture of what's going on here, because this is what's going to connect, or like I have a demonstration, a simulation of how we connected this to series circuits to parallel circuits in the next lesson. So I have this little demonstration for you on this other. There it is. All right. So here's the demonstration. I've gone ahead and drawn the circuit diagram for you, right? So we have our battery here up at the top. We've got wires connecting. These little symbols down here are actually light bulbs. Now remember the first day that I told you with resistors that resistors, there are actual things that are resistors and just have resistance, but they also represent anything you could put in a circuit, like a light bulb or a fan, an appliance of some kind. All of those have resistance, and so we can just generalize them as resistors. But this is a little symbol for a light bulb, and you'll see why I actually have the light bulbs here in a moment. But yeah, this simulation is super cool. It's the circuit construction kit on fet.colorado.edu, so you can check that out if you have some spare time or you want to. It's really neat. You even have, so I've got the current showing off right here, but you can actually show the current. It's got the electron flow, right, going from the negative side to the positive side, so that makes sense. It's got the regular conventional flow also, going from positive to negative, and you can show that as well. Of course, that's a lot of motion on the screen, so I'm gonna turn that off because it's kind of a lot. All right. So this has another neat feature here. Real quick before I show the battery, or what I came here for, I guess. You've got an ammeter and a voltmeter that you can use. So an ammeter measures the current, right? It says current on there. You can see that. So all you do with an ammeter, we would get to do this if we were in person, but we can't because we're all separate. An ammeter goes into the circuit. So you can, I'm going to make this little split right here. You stick it in the circuit and it measures the current flowing through it. So that's ugly. You see that the current flowing through here is 2 amps, right? That agrees with the work that we did. Heck yeah. And that's the same. If you stuck it anywhere else, it'd be the same, right? Because the current doesn't, it just all flows through this little path. Our next thing is the voltmeter. Voltmeter measures voltage. Surprise, surprise. Now it's got this little red lead and a black one. What you do is you take the red lead and you stick it on, if you've messed with like a car battery or something else, this shouldn't be a surprise, but you take the measuring the battery here. You can set the values of these resistors, by the way. I should have said that before, that I've got this one is 10 volts, you can see, and this one's the 4, and this one's the 1. So I made the circuit we were just using. So that's why the 2 amps agrees. I should have made that point before. So you take the red lead and you stick it on the positive side. So like the higher voltage side, I guess, is the positive side. And which would be this side, right? Because the flow is coming this way and then it drops going this way. So this side, this left side, is the positive side. It's the higher voltage side. And then you take the black side and you put it on the low voltage side. Boom. So this is our 4 ohm resistor, and you see that it's got 8 volts across it. Heck yeah. We can measure the other one too, right? Stick it here on the positive side, stick the black one here on the negative side, a 2 volt drop. Checks out, right? That backs up our math. Lovely. You might have noticed too for a second whenever I had this here, right? You see that there's a 0 voltage drop from here to here, which is like what we said, right? Where the voltage doesn't drop across a wire, so we should have no voltage difference here, which is pretty neat. But yeah, that's what's going on here. If you were curious as to what you do, what happens if you change the direction, you put them on the opposite side, it reads as a negative voltage drop. It's reading from the red to the black, right? And so we actually have a voltage increase if we're going this way across the circuit. That's why it reads negative, because voltage is a drop, but this one's getting an increase. So that's why it reads negative there. So yeah, that's the voltmeter and the ammeter. Lots of fun to play with. I'll leave the ammeter, I guess, in a second. But back to what I was originally doing with this. Sorry, this is very cool. You can do a lot with it. This is the symbol mode, but you can turn it to real life mode by clicking this. So yeah, we've got the battery here and our 2 light bulbs. Now, the light bulbs have these little yellow lines coming off of them, which has to do with the brightness of the light bulb, right? So we can see very, very clearly here that our 4 ohm light bulb is much brighter than our 1 ohm light bulb, right? And that has to do with the voltage across the light bulb. So if there's a higher voltage drop, which we know that there is across the 4 ohm resistor, then, or the 4 ohm light bulb, if it's a light bulb, the larger voltage drop means more light, and you have less light over here on the just 2 volt drop. This idea becomes really important when we get to parallel circuits, because something a little bit different happens with them. But yeah, this is something that goes on with series circuits. If things are hooked up in series, you get a darkening effect because the voltage drop is different across one than the other. So yeah, that's the simulation there. We'll pop back and look at just our next problem, I guess. Let me erase. Okay. So our next problem, the idea here is pretty much simple, straightforward, and it'll be the same. I just wanted to show you another problem. This one, for example, has 3 resistors in it. So let me draw it up real quick. Right, we have 1 resistor here, 1 resistor here, 1 resistor here. And that's 12 volt battery. 2 ohm, 3 ohm, 1 ohm. All right. So part A, just what is the equivalent resistance? equivalent resistance is you just add them all up, right? R1, this is tedious at this point, I guess, because it's just addition, right? But writing it out, R3. R1 is 2 plus 3 plus 1. So our equivalent resistance very clearly is just 6 ohms. All right. Part B. What is the current running through the 3 ohm resistor? This one specifies here, right, that it's running through the 3 ohm resistor. But remember, the current doesn't change here, right? It's going through the same wire. The current doesn't go anywhere. So it's the current that's flowing through all of these is how you do that. But remember that we're looking for, basically, you can't just use this 12 volts and the 3 ohm resistor, right? Because the 12 volt drop isn't like all across this, right? We drop some on the 2 ohm, we drop some on the 3, and we drop some on the 1, and all of those add up to 12 volts. So our voltage across this 3 ohm resistor is not 12 volts, right? It's some portion of that. But remember, we can use the equivalent resistance to make that equivalent circuit, right? And find the voltage across that, which would be 12, and use that to find the current, just like in the previous problem. If that sounded confusing, it's just like in the previous problem. I'm sorry. So basically, we can find current using the equivalent resistance, right? V equals I R. I'll even specify IR EQ here, right? Because this is the full voltage, the current through any of them, times the equivalent resistance. That's how we find the total current flowing through all of it. So our voltage is 12 volts. We're looking for current, current, that's what that is. And 6 ohms is our equivalent resistance. Divide by 6, right? 12 divided by 6 is 2 amps. Bad A. All right. 2 amps. Part C, what is the voltage across the 3 ohm resistor? Just the 3 ohm resistor, this one. See? So our current through all of these is 2 amps, so we can look at just this 3 ohm resistor. We know resistance, we know current, so we can find voltage. Right? V equals IR. Voltage is what we're looking for. Our current is 2 amps again. Resistance is 3 ohms. 2 times 3. This math is really hard in this one, right? 6 volts. Lovely. Boom, that's our voltage. Easy peasy, right? You guys got this. I believe in you. Very straightforward. Again, circuits aren't scary. Circuits are neat. So yeah, go do that exit ticket. Ask me if you got questions. All the above. Stay warm.